In this video, we'll tackle a really important type of concept in statistics and probability, and this really dominates statistics, and it's an extremely useful way for companies to look at things like profitability, and insurance companies to look at things like whether they're charging enough premium, and that applies to any type of insurance, or even a warranty plan is considered insurance. So. A probability distribution is something that describes the way in which probabilities are allocated or distributed to every value of a random variable. So when I think about this definition, what occurs to me is something very visual, and so every value of a random variable, for example, let's see, where did my pen go? I would say that, let's just say I have a random variable that is x, and the value can take on one of three possibilities. Now, what is a random variable? Well, a random variable isn't, you can't just ignore the word random. It literally implies that the variable takes on values randomly. That is, we can often pinpoint the possible outcomes. We know maybe what values x can take on, but we cannot be absolutely certain which outcome will take place. So a probability distribution would say, all right, well, x, suppose, can take on the values 1, 2, or 3, and it'll take on the value 1 with probability 20%, and it'll take on the value of 2 with probability 60%, and it'll take on the value of 3 with probability 20%. So that is to say, we want to count for 100% of all the different possibilities. So our probabilities of all the different values of the random variable should always add up to 1. That's a key thing, because otherwise we haven't fully described the probability distribution. And so a probability distribution can be summarized by a table. So there's nothing really fancy about this, or by a histogram. And a histogram is really just a fancy type of bar-like graph that displays the events, the possible values of x, on the horizontal axis, and their associated probabilities on the vertical axis. So we can do that in one of two ways, and oftentimes we see it in the latter form as a histogram, because oftentimes some random variables, like for example a continuous random variable that can take on continuous values between, say, 1 and 3, can have infinitely many possibilities, and so oftentimes you see something that is more in the form of a histogram versus a table, because it'd be impossible to summarize infinitely many values that way. So consider a single die roll. Let's start with an example. Give the probability distribution of x equals the value of the side facing up after the roll. Okay, so first of all, let's think about what x actually means. So x is the value of the side facing up after the roll. So you roll a die, and here's your die, and I'm not very good at drawing three-dimensional objects, but some of them have, each side has different number of dots facing up. That's actually not too bad, is it? We know that x can take on one of 6 possible values. The value that shows up after the roll is 1, 2, 3, 4, 5, or 6. Now, it can't take on all these values simultaneously. We're just saying that x takes on one of the values in this set, 1 through 6. Okay, well, if I were to summarize this in a table, I would say, okay, what is x, and then what is the probability of that x value? All right, well, we can have 1, 2, 3, 4, 5, or 6. Those are the sides that can come up. And what do we know? Well, if this is a fair die, then we know that each of these represents probability 1/6. They are equally likely, and so each one has, since there are 6 possibilities, any given event has a 1/6 chance of popping up. And we're pretty familiar with that. And so now a histogram would display the different values of x. So in this case, 1, 2, 3, 4, 5, or 6, and then the probability of x on this side. So it's kind of like just graphing a function. So we now can take our probability, which we know is 1/6 across the board, and we can draw these bars. And typically with a histogram, you have the bars touching. So we'll just say that bar represents 1, that bar represents 2. They're supposed to be equal width, so let's try this again. So maybe we'll have 1 be between there, and 2, and 3, and 4, and 5, and 6. So all of these bars would be uniform, so I'm just going to draw a straight line across, and then I'll individualize the bars. And so probably Well, it would look like this, right? This would be a way to graph it, and this gives us an idea of what we would expect. So we would expect that all of these events are equally likely, and so it doesn't matter what number we pick on the die, we're always going to have the same probability of our number coming up. So that's the basic idea of a probability distribution, both visual ways to represent that. So let's take a look at another example. So a health insurance company determines that a client files a medical claim with probability 0.21, 2 medical claims with probability 0.14, or 3 medical claims with probability 0.07. An insured may not file more than 3 claims. Give the probability distribution of X equals the number of claims a client files. Alright, well, let's jump back here for a quick second. One note here is that if you add up all these probabilities, we get 6/6, which is equal to 1. So we've got to make sure that when we define X, that we accumulate all the probabilities. Well, here it shows that X can be 1, 2, or 3. And now if we come over here, and this is just the number of claims a client files, so they can file up to 3. And naively, if we put 1, 2, and 3 here, and then the probability that you file that many claims, so the probability that you file 1 claim is 0.21, probability that you file 2 medical claims is 0.14, or 3 medical claims, the probability is 0.07. Now when you add these up, these 3 sum up to 0.21 plus 0.14 plus 0.07 is 0.42. So as you notice, these don't add up to 100%, which is what we need down here. Well, what else are we missing? Well, it didn't say it here, but a person doesn't have to file a claim. If you think about it from this practical standpoint, as an insured, you may not file any claims at all. So that must mean that if you can't file more than 3 claims, that you could file 3, 2, 1, or 0. And so if there's a 42% chance that you file 1 or more claims, then that means there is a 1 minus that, which is 0.58, or 58% chance that you don't file any. So with our probability histogram, we can again list 0, 1, 2, 3, and we'll just again list these as separate bars. And now we can take a look at the probabilities, which I'll just go up in increments of 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. And then we know that the probability of filing 0 claims is the highest. Probability of filing 1 claim is 0.21. Probability of filing 2 claims is even smaller, and the probability of filing 3 claims is even smaller than that. So what can we tell here? Well, if we look at this probability distribution, we know that we can immediately say, well, there's a really low likelihood of filing a lot of claims, but a very high likelihood of not filing any, and then the probabilities go down as you move over. Now, if this were a continuous distribution, in other words, I know you can't file anywhere between 0 and 3 claims continuously, like you can't file 0.1 claims, but if this were a continuous distribution, a lot of times you'd see this as a continuous curve sort of being overlaid over the top of these, and instead of actually seeing the bars, people will use this continuous curve. Now that has to do with calculus, and you're probably introduced to maybe integrals or antiderivatives at some point. This actually represents infinitely many little tiny rectangles placed under this, so it kind of looks like a continuous curve. But nonetheless, that's just to help you maybe draw the connection. So let's do another example. Consider an NBA player who is about to shoot two free throws. He has a record of making a free throw with probability 90%, independently of any other shot, I should say. Give the probability distribution of n equals the number of free throws he makes in his current opportunity. All right, well, so the number of free throws he makes, well, he's going to shoot 2 of them. So that means he could make none of them, he could make 1 of them, or he could make both of them. And so, again, we could take a look at the probability distribution of 0, 1, or 2. Now, we know there's a 90% chance he makes a free throw, but we know he's taking 2 free throw shots. So the probability that you make a free throw, we'll just say the probability that you make, is equal to 90%. And this is just one free throw, right? So we're talking about shooting 2 of them here. So the probability that you don't make, and I'll just say make with the bar over it, would be then 10%, right? So if there's 90% chance that you do something, there's a 10% chance that you don't. Now, what are the outcomes? Well, the outcomes are he takes the shot, and this is free throw 1. Well, he either makes or he doesn't make. And then for free throw 2, he either makes or he doesn't make. So here's where our counting comes in pretty handy. And same thing if he misses the first one. So basically what we have here is make, miss, make, or miss, miss. And these aren't all equally likely events, right? In other words, you can't just say that these are 1/4, 1/4, 1/4, 1/4, because the probability that he makes both of them is higher than the probability that he misses both of them. There's only a 10% chance that he misses and a 90% chance that he makes. Well, since these events are independent, we could list the probability of each of these events. So make and then make again would be 90% of 90% of the time he would make both of them, which would be 0.81. The probability that he makes and then misses is 0.90 times 0.1, which would be 0.09. The probability that he misses and then makes is 0.1 times 0.9, which is again 0.09, just in reverse order. So same event, just different order. And you can't just omit this one. Some people will say, well, can't I just go ahead and omit one of these since it doesn't really matter which order he makes them in? But if you do that, watch what happens. Now this is 10% times 10%, since miss is really unlikely. There's only a 1% chance that he misses both of them. But now if you add up these probabilities, 0.81 plus 0.09 is 0.9, 0.9 plus 0.09 is 0.99, and this gives us the whole of 1.00. If we had just pretended like one of these didn't exist and we said, hey, these two are the same, then we would have been off by 9%. So even though we may not care about the order in which he makes them, they are different outcomes, and we do need to record those. Okay, well, n can be 0, 1, or 2. So coming back to this over here, now that we have this diagram, we can really easily go in here and say, well, what is the probability that he makes 0 free throws? Well, what does that mean? Well, that means that he misses both free throws, right? If he makes 0 of them, then he misses both of them. Well, we know there's a 0.01 chance of that, so the probability of n. To make one of them, that occurs in two potentially different ways. He makes the first, misses the second, or he misses the first and makes the second, and that's 9% for the first one and 9% for the second one. So there's a total of an 18% chance that he makes exactly one. It's either he makes the first one or he makes the second one, but not both. And then the probability that he makes both free throws, well, that's this event here, make, and that's 0.81. And now if you add these up, this should be apparent that this adds up to 1, because basically each one of these 4 outcomes gets bucketed into one of these 3 scenarios here. And so now we can draw a probability distribution, or histogram, and we can visualize this. So the probability that you get 0, 1, or 2, well, there's a really, really low chance that you get the, and I won't label the y-axis here, but really low chance that you make 0 of them, a little bit higher that you make 1 of them, and really high that he makes both of them. So if a statistician was analyzing the statistics on this basketball player, then he'd probably put his money in on the fact that he'd bank his money on the player being able to make both of the free throws. At least, it's almost guaranteed that he makes at least 1 point. So if the team needs at least 1 point, they know they can pretty much count on this guy. So that's it with probability distributions. Of course, these can get more complicated, more sophisticated, but this is just an introduction, so hopefully this gives you a little bit of motivation behind how these things can be used and how they can be useful in having us assess uncertainty in events.